Welcome back to my channel. We are facing a very difficult situation in India. Now, every hospital are full of patients. Everywhere so painful and so fearful. Each one are facing difficult condition. But we need to take care ourselves. We need to face the problem and we have to emotionally strong and faith in God. I know the problem practically because my father also expired 14 August 2020 in heart attack. We know the problem. Practically, I could not get my father to visit proper doctor because for COVID situation and for lockdown, every chamber in this time was closed. My father told her heart pain, but in this situation, every chamber was closed. So I could not see him proper doctor observation because this time lockdown was very strict. I know the problem. So pray for those men who died in COVID situation. Now let's come back in subject. In my previous video, I have classified finitely generated abelian group. But what will be the structure of finite non-abelian group? Finite non-abelian groups are much harder. Its structure is just mysterious than the abelian group. And Sylow's theorem gives the structure of any finite subgroup. Actually, Sylow tells about what finite groups are there. If you fix the order of any group, in your mind can arise a question always, how big are its subgroups? How are those subgroups are related? And how many subgroups are there? Are any of them normal? And you will get all questions if you know the Sylow theorem. In my earlier video, I have seen the Lagrange's theorem. If A is be a subgroup of G, then order of A is must divide the order of the group. But converse of the Lagrange theorem always not true. That means if M divide N, N means order of the G, then it does not imply there exists a subgroup A is with order of A is equal to M. As for example, we all of us know in A4, order of A4 equal to 12 and 6 always divide 12. But there exists no subgroup in A4 of order 6. Sylow's first theorem gives the partial converse of Lagrange's theorem. Sylow's theorem tells if G be a finite group and P is a prime number such that P to the power R divides order of the group, that implies G has a subgroup of order P to the power R. That means if PQ divide the order of the group G, then G has a subgroup of order P, P square and PQ. Okay? Consider order of G equal to 8. And note here 2 is a prime number. Then, since 2 to the power 1 divide 8 and 2 square divide 8 also, 2 cube divide 8. So, by Sylow theorem, it can tell there exists a subgroup of order 2, 2 square and 2 cube. Are you getting the Sylow theorem? Well, recall Cauchy's theorem. If P is a prime number and P divides order of the group, then there is a subgroup of order P which is cyclic and has no non-trivial subgroup. Then G contains an element of P. And first Sylow theorem tells if P to the power K divides order of the group G, then there exists a subgroup of P to the power K which has subgroup of order 1p square up to p to the power k. Then G might not contain an element of order k. That means actually first Sylow theorem is a generalization of Cauchy's theorem. Now consider the group of order 200. We all of us know this is equal to the power q times 5 square. And by Cauchy's theorem, we can tell G has an element of order 2. Also, G has a subgroup of order 2. This is actually the subgroup of order 2. And by Cauchy's theorem, we can also tell G has an element of order 5. That means G has a subgroup of order 5. This is the subgroup of order 5 and this is the subgroup of order 2. That means their intersection always will be subgroup. That means cyclic subgroup generated by A intersection cyclic subgroup generated by B always will be identity. Are you getting? This is the intersection. And by first Sylow theorem, we can tell G also have a subgroup of order 25. Are you getting? This is the subgroup of 25. And G also have a subgroup of order 4 and 8. This is the generalization of Cauchy's theorem. Are you getting? Well, and the special case of Sylow theorem is if G is a group of order p to the power n times a, where p is a prime number, and if p does not divide m, then G has a subgroup of order p to the power n. Are you getting? Well, now let's see other definition. Maximal p subgroup or PSSG. Suppose order of A is equal to p to the power m and p to the power m plus 1 does not divide the order of the group. Then A is called p Sylow subgroup or PSSG or maximal p Sylow subgroup. That's one example. A4. We all of us know order of A4 equal to 12 and K4 is a subgroup of A4. Here the order of K4 equal to 2 square and 2 square divide 12, but 2 to the power 2 plus 1 means 8 cannot divide 12. So K4 is a 2 SSG. Are you getting? Okay. Also there is this other subgroup A is in A4 when A is isomorphic to Z3. And here notice 3 also divide 12, but 3 to the power 1 plus 1 which is equal to 9 cannot divide 12. So Z3 is a 3 SSG. Okay? Well, I hope my all viewers have understood what is the Sylow P subgroup. Now let's see Sylow's second theorem. Sylow's second theorem states, let G be a finite group and P be a prime number which divides the order of the group. Then all Sylow P subgroup are conjugate. That means if P1 and P2 are Sylow P subgroup, then there exists small g in capital G such that G P1 G inverse equal to P2. Are you getting? Well, one example S3. We all of us know this is the structure of S3 and order of S3 equal to 6 which is equal to 2 times 3. And H1, H2, H3 are subgroup of S3 and these subgroup are 2 SSG of S3 because 2 divides 6 but 2 to the power 1 plus 1 does not divide 6. So here H1, H2, H3 are 2 SSG in S3. Are you getting? Well, Then by Sylow's second theorem, we can state by Sylow's second theorem, we can state H1, H2, H3 are conjugate. Let's check one. Consider H1. That means H1 equal to E12 and choose G equal to cycle 1 3. Now G H1 G inverse, which will be 1 3 times identity 1 2 times 1 3. After operation, it will be 1 3 1 3 1 2, here inverse 1 3 inverse. Okay, if you calculate this will be check on self. This is equal to 1 2 3. If you check the inverse, then this will be also 1 3, and after multiplying it will be identity 2 3. Okay, and this is equal to actually H2. So H1 is a conjugate to H2. Okay, well, now I will mention one corollary. Suppose a group G has only one Sylow P subgroup, which is capital H. Then A must be normal in G, and this proof is very important. Try to oneself. In S3, A3 is unique Sylow 3 SSC. So in S3, A3 is a normal subgroup. Actually, this corollary is very useful to find normal subgroup. Now let's see the third Sylow theorem. Third Sylow theorem tells about the number of Sylow P subgroup. This theorem states, let G be a finite group and P be a prime number that divides order of the group. Write G equal to P to the power E times M, where P does not divide M. Then S be the number of Sylow P subgroup of G. Then it implies two conditions. Condition 1, S divides M, and condition 2, S equal to Pk plus 1, where for all K belongs to natural number. Are you getting this theorem? That means when you divide S by P, then the remainder will be always 1. Now let's see this group of order 200 again. Here the number of 2 SSC of order 8 and 5 SSC of order 25. That means N2 should divide 25, and this is equal to actual 2k plus 1 equal to 25, and this is possible for k equal to 1, 5 and 25. So we can tell there exists 2 SSC, number of 2 SSC of is are either 1 or 5 or 25. Okay, and since order of 5 SSC equal to 25, that means N5 should divide 8, and that implies 5k plus 1 equal to 8, which is imply k equal to 1. That means number of 5 SSC here 1. Are you getting? That means N5 here is a normal subgroup. We all of us know. If I consider there exists a subgroup which is D4, this is actually 2 SSG because the order of D4 equal to 8, and we all of us know all other 2 SSG are conjugate to each other. So other 2 SSG cannot be either C8 or C2 cross C4 or Q4. Are you getting? Because these are not isomorphic with D4. This is the actual structure of this group. Are you getting why the Sylow theorem is important to construct any group of order? Now classify the group of order PQ, where P and Q are distinct prime and P greater than Q. Observation 1. Suppose G is an abelian group of order PQ. Then by the structure of finite abelian group, we all of us know G is isomorphic to direct product ZP, direct product ZQ, which is isomorphic to ZPQ. Hence ZPQ is an abelian group of order PQ. And any abelian group of order PQ is isomorphic to ZPQ. Now consider G is non-abelian group of order PQ. Suppose G is non-abelian group of order PQ. Let NP denote the number of Sylow P subgroup and NQ denote the number of Sylow Q subgroup. Okay? Then by Sylow theorem, by third Sylow theorem, we can tell NP equal to 1 plus Kp and NP divide PQ. That means 1 plus Kp divide Q. And since P greater than Q, that means 1 plus Kp is only equal to 1. So there exists unique Sylow P subgroup in G. Again by Sylow third theorem, NQ equal to 1 plus KQ and NQ divide PQ. That means 1 plus KQ divide P also. And that implies 1 plus KQ equal to 1 or 1 plus KQ equal to P. And for this line, it implies NQ equal to 1. And from this line, it implies NQ equal to P. Okay? If NQ equal to Q, if you consider, then Sylow Q subgroup is unique. Now consider capital P and capital Q denote the Sylow P subgroup and Sylow Q subgroup respectively. Then G equal to P direct product Q. And since P and Q are Sylow P subgroup and Sylow Q subgroup respectively and which are unique, so they are normal in G. That means P is isomorphic to ZP and Q is isomorphic to ZQ. So we can tell G is isomorphic to ZP direct product ZQ. Since PQ are prime, which is also isomorphic to ZPQ. And that implies G is abelian. But this is the contradiction because our assumption G is non-abelian. So NQ cannot be 1. NQ always will be P. That means 1 plus KQ equal to P and that implies KQ equal to P minus 1. From this line we can tell Q divide P minus 1. So G is non-abelian if Q divide P minus 1. And this part is very important to find the structure of a group. And this part also important for any competitive exam to find quickly is the group is abelian or non-abelian. Further, suppose P is a unique Sylow P subgroup of G and Q is a just Q subgroup. Since P is a unique P subgroup, that implies P is normal. Thus, PQ is a subgroup of G. And we all of us know, since P is a Sylow P subgroup and Q is a Sylow K subgroup, So P intersection Q also will be subgroup of P and Q. So P intersection Q, order of P intersection Q should divide order of P, and order of P intersection Q should divide order of Q. Since P and Q are both prime, that means order of P intersection Q must be 1. Okay? And we all of us know this theorem. Order of PQ equal to order of P times order of Q divided by order of P intersection Q. And since order of P intersection Q equal to 1, that means this is equal to just PQ. So, order of P intersection Q equal to order of G, and order of PQ contain G. That means G equal to P times Q. Also P be a normal subgroup in G. So by definition of semi-direct product, G is isomorphic to P semi-direct product Q, where P is isomorphic to ZP and Q is isomorphic to ZQ. Therefore, in this observation, I will construct a non-abelian group of order PQ, which is isomorphic to ZP semi-direct product ZQ. Are you getting the construction? Are you getting the importance of Sylow theorem? If you know the Sylow theorem properly, then you can find any group. In this observation, I will construct a non-abelian group of order PQ. Let PQ be distinct prime such that Q divide P minus 1. Now consider A is equal to ZP and K equal to ZQ. Then we all of us know automorphism of A is equal to automorphism of ZP, which is isomorphic to UP, and UP is similar to ZP minus 1. Since Q divide P minus 1, so Q is a divisor of the cyclic group. So suppose A is unique cyclic subgroup of automorphism A of order Q. Okay? Now we can define a isomorphism from ZP to L, which contain automorphism of A's. Now consider a homeomorphism phi from K to automorphism A's, where K is ZQ. This is a always group homeomorphism. So by definition of external semi-direct product, G is actual isomorphic to ZP direct product ZQ. Okay? There is a nice result. Consider order of G equal to PQ, and if P does not divide Q minus 1, where P less than Q, that implies G is cyclic. Consider the group of order 15. Here notice this is equal to 3 times P, 5, and here 3 does not divide 5 minus 1. So the group of order 15, that means G is cyclic. Are you getting? Similarly, group of order 35, 65, 91 are both cyclic group. So this result is very useful for any comparative exam. So group of the form PQ where P less than Q. Case 1. If P does not divide Q minus 1, then up to isomorphism there is only one group, which is ZPQ. And case 2. If P divide Q minus 1, then up to isomorphism there exist two groups. One could be this group ZPQ and other is non abelian group ZP semi-direct product ZQ. Now let's see the group of order 2P where P greater than equal to 3. When the group will be abelian, then G is isomorphic to ZP, and when the group will be non abelian, then G is isomorphic to DP where P is a odd prime. Therefore, up to isomorphism, there exists two groups, one abelian and other non-abelian. Let's see. For non-abelian group. Now consider for a non-abelian group of order 2p. Order of G equal to 2p. That means there exists 2 Sylow subgroup and p Sylow subgroup. And order of 2 Sylow subgroup 2SSG equal to 2 and order of PSSG equal to p. Then number of 2 SSG would be 1 plus 2k, which should divide p. That means that implies this is either 1 or p. And number of PSSG is 1 plus pk. That means PSSG is unique. That implies this is always normal. Okay? So, G is not a simple group. So, the number of elements of order p in PSSG, since p is odd prime, this is always equal to phi p, which is similar as p minus 1. Okay? And number of 2 SSG always will be p, because I have considered the group is non-abelian group. Since the number of PSSG is 1, so number of 2 SSG must be equal to p, because if it is equal to 1, then the group will be cyclic. That means number of 2 SSG for the non-abelian group is p. Since the number of element of order p in PSSG p minus 1, so the remaining element in G will be 2p minus p minus 1, which is also equal to p plus 1. Since in group always exists identity, so number of element of 2 SSG of order p will be actually similar to p. Okay? And this structure is similar to DN group. So, this is isomorphic to DP. Now, let's see group of order 34. We all of us know 34 equal to 2 times 17. Here 17 greater than 3. So, we can tell easily this is isomorphic to either Z34 or D70. Are you getting? If you know the Sylow theorem easily, then you can construct the group easily.